Hey guys, how you doing? This is Art Scott, Coach Scott. Yeah, and we're here to talk about vapor pressure. Sorry, something popped out on my Apple Watch and it caught my attention. So anyway, this is Coach Scott. We're going to talk about our fourth video in a series on intermolecular forces. Let's talk about vapor pressure. Okay, and we might change some of our opinions about some things that we know exactly what's going on. So, what is boiling? Well, boiling and evaporations are two ways in which a liquid can vaporize into a gas. So boiling is a way to vaporize a liquid. Now, there's some distinctions between these two processes. Boiling occurs at a specific temperature. We call it the boiling point, or the BP, which is a physical property of the substance. Now, evaporation will occur below the boiling point. So it's trying to turn into a gas, but it does not have to reach the boiling point to do that. Now, boiling will occur throughout the entire liquid, whereas evaporation will only occur at the surface of the liquid. Now, here's the definition of boiling. You ready? Boiling is when the atmospheric pressure equals the vapor pressure of the substance. Not at 212 F. Not when there's a bunch of bubbles, but when the atmospheric pressure equals the vapor pressure of the substance. So, what is vapor pressure? Now, this is related to IMFs. So, vapor pressure is the pressure exerted by the gas molecules above the surface of the enclosed liquid. Now, if I look at sample A, this is a lower temperature. That's what this means here. T2 is greater than T1. Now, there's some liquid, right, that is above, some of those molecules are above the surface of the liquid. All right? Now, when I increase the temperature, all right, there's a greater number of vapor particles above the surface of the liquid. That's going to increase the vapor pressure of the liquid. Okay. So, some properties of the liquid. All right. Volatility is another characteristic of that liquid that's based on the characteristics of its intermolecular forces. Now, the more volatile a liquid, the more quickly it will evaporate. It's going to have a higher vapor pressure at a given temperature, and the weaker its intermolecular forces are going to be. Now, we'll use acetone to dry glassware in a chemistry lab. What do you think instead of water? Well, it's much more volatile than water. It will evaporate very quick. All right, which is why we use acetone. Have you ever fingernail polish remover? Yeah. Now, at any temperature, some molecules in a liquid will have enough energy to escape. And that's what we mean by the evaporation. As I increase the temperature, the fraction of molecules that have enough energy will increase. So here I've got a substance. All right. And this is a measure of the kinetic energy. And then we can see the temperature. There's two different temperatures here, right? So at a certain energy point, E sub 0, all right, I have more molecules that have enough kinetic energy to escape the surface or escape the hold of those other molecules, holding them inside of that liquid. So the purple dot, or the purple line, is at 300 degrees K. The green one is 100 degrees K more, or 100 degrees more, and you can see that, okay, it's a little lower, but I've actually increased the amount or the number of molecules that have enough energy to escape the surface of that liquid. So, as more of these molecules escape, the pressure that they exert will also increase. So as pressure increases, okay, and pressure is a measure of force per area, right? There's going to be pushing down more on the surface of that liquid. Now, eventually, the liquid and the vapor will reach a state of dynamic equilibrium. That means as a molecule will escape and evaporate, another vapor molecule will condense at the same rate. If one goes out, another one goes in. That's what we mean by equilibrium. We'll come into that later. Now, these are vapor pressure curves. Back when we had an EOC, you'd probably see one of these on the EOC. Now, these curves are an infinite number of points. You've learned that in algebra. So each point along that curve shows what the temperature is at that atmospheric pressure, or when the atmospheric pressure equals the vapor pressure. So the y-axis is vapor pressure in torr, that's a unit of measurement of pressure, and temperature in degrees C. So anything above this, okay, is going to boil. It's higher than the atmospheric pressure. So I've got ether, I've got ethyl alcohol, water, and ethylene glycol, antifreeze, right? So any point above that curve indicates what the boiling point is. So if I look at water, right, 760 or torr is the normal atmospheric pressure. If I move along that line, it intersects the water, all right, temperature at 100 degrees. So that means any temperature above 100 degrees, the water it's going to boil because the atmospheric pressure equals the vapor pressure. Okay. So I can also adjust the pressure. If I increase the pressure, what happens to the boiling point? It increases. If I decrease the pressure, what happens to the boiling point? It goes down to about 90 degrees C. So if I can get my pressure down to almost zero, right, it's going to boil, well, at normal room temperature, right? If I'm almost in a vacuum, I can boil water. I wonder if we can do that in the class. We'll see. Okay. I'm sorry, I thought I had a little yellow circle around. So, the boiling point is when the vapor pressure equals the atmospheric pressure. All right. The normal boiling point is the temperature at which the vapor pressure is, normal atmospheric pressure is around 760 millimeters of mercury, or 760 torr. So that means the boiling point of diethyl ether is 34.6, so on and so forth and so on. All right. So this is what you need to know for any type of testable material, and they have seen these on ACT. So what is the normal boiling point of ethanol? Well, I'm looking at my normal atmospheric pressure, 760. Ethanol is right there, so it would be 78.3. That would be D. Not too hard. Know how to read these graphs. What is the boiling point in degrees C of diethyl ether there at 200 torr? If I go right there, whoa, it's almost like zero. So I'd probably say that was, I'd call it zero. That's what it is. Okay. What's the boiling point of water at 300 torr? Well, that's about 300 torr. Let's go find it. Wow, that's going to be what, about 75? Yeah. Yep. So, some of your parents may have got something cool, all right, for Christmas. They might have got an Instapot. Magical, brand new technology. No, it's not. My grandmother used to have something like this. It was a pressure cooker, all right, because a liquid will boil when the vapor pressure, remember that's what boiling is, equals the atmospheric pressure. So how an Instapot or a pressure cooker works is they're increasing the atmospheric pressure, or the pressure inside the pot. So the water is not going to boil at 100 degrees C. It can be heated up to 120 degrees C before it begins to steam or boil. Wow. So by raising the temperature, that's what cuts the cooking time, right? Instead of cooking at 90 degrees C or whatever, you're cooking at like 300 at Fahrenheit or 120 degrees C. Pretty cool, eh? Old technology, we'll relabel it and call it something cool. So, I'm sorry, I said 300. 250 degrees pressure cooking temperature. All right, there's normal boiling temperature. So I increase the pressure, this heat, all right, in this pressure sealed vessel will cook the food faster. All right. So you can cook a whole chicken in like 15 minutes where it would take you a whole hour. Black beans in 15 minutes instead of 60 minutes. Wow. So, recall this, that boiling is what? When the vapor pressure equals atmospheric pressure. Since the atmospheric pressure is so low at high altitudes, like in Denver, Colorado, or top of Mount Everest, the water will boil at a much lower temperature than here in Memphis, Tennessee. All right? So, we have to cook stuff longer when we're on Mount Everest. And we're going to do something in class. We'll see if we can't boil some water at room temperature. I bet you we can. Okay, guys, this is Coach Scott saying, have a good night and keep learning about chemistry.